A wire is a conductor which has free moving electrons. These electrons carry electric charges. If the wire is not connected to a battery, these charges will move in random direction. This means there is no preferred direction for this flow of charges. A battery provides the energy for these charges to flow around the circuit. The flow of charges in a preferred direction is called an electrical current. We just call it the current. Note that there are two types of current flow. One is conventional current flow, where the current flows from the positive end of the battery to the negative end. The other is the electron current flow, which flows from the negative end of the battery to the positive end. From now on, when a current is mentioned, it means the conventional one. Note that the symbol for current is capital I. When the current flows in one direction around the circuit, we call it a direct current. Such a circuit is called a DC circuit. When the battery provides current that changes direction at every interval of time, we call it an alternating current. Such a circuit is called an AC circuit. We won't be covering AC circuit. Please take note. For there to be a current, there has to be an energy source to move the charges around the circuit. This energy source is provided by the battery, and this energy is called EMF, or electromotive force. The EMF of a battery or any other electrical energy source is the energy that the battery delivers to a unit charge to move around a complete circuit. Please note that EMF is not a force. It is energy per unit charge. Its SI unit is volts. Let's attach a light bulb to our circuit. Now we know that the light bulb will light up and gives off heat. So where did the light bulb get this energy from? The energy provided by the battery to the charge will be transferred to the light bulb. The light bulb will convert the electrical energy to heat and light energies. But how much energy does the bulb get from the battery? If the battery supplies an EMF of 2 volts to every unit charge, then the light bulb will receive 2 volts from every unit charge that passes through it. All of this is simply the conservation of energy. Recall that the electrical energy provided by the battery to every unit charge is called the EMF. And the energy received by the light bulb from every of these unit charge, which is then converted to other forms of energy, we call it potential difference. The EMF must be from a power source, and whatever energy that is converted to other forms of energy, we call it potential difference. So what is the difference between EMF and potential difference? Both have the same SI unit, which is the volts. However, EMF is the electrical energy from an energy source like the battery. Potential difference is the amount of that electrical energy which is converted to other forms. One example that we have been using is the light bulb, which converts the electrical energy to heat and light. To measure the EMF of a battery, we connect a voltmeter parallel to it, as in setup A. And if we want to find the potential difference of the light bulb, we connect the voltmeter parallel to the light bulb, as in setup B. Now, if we want to measure the current that flows through the light bulb, we just connect the ammeter directly beside the light bulb, as in the third setup here. Now, let's replace the light bulb with a resistor. A resistor is drawn like a rectangular box, and on the right that's how a resistor looks like. So what is a resistor? It's just a device which resists the flow of current through it. And just like the light bulb, if the battery has EMF of 5 volts, the resistor will also have a potential difference of 5 volts. If we know the current that flows through the resistor, and if we know the potential difference of the resistor, we can calculate its resistance. Its resistance, labeled by capital R, is just potential difference V divided by the current I. And the SI unit for resistance is ohms, with the symbol given here. Let's look at one example. Now observe the following circuit. If the battery has an EMF of 10 volts and the current flowing through the resistor is 2 amperes, what is the resistance of the resistor? Using the formula R equals to V over I, we get 5 ohms. So why is V 10 volts? It's because the EMF and the potential difference are the same here. Now, what if we have the following circuit, where we have two resistors R1 and R2 connected side by side? Will the current flowing through each resistor be 2 amperes? Will V1 and V2 be equals to 5 volts? What do you think? Or something like this, where we have two resistors R1 and R2 which are connected in parallel. Will the current flowing through each of them be 2 amperes? Or will the potential difference V1 and V2 be 5 volts? What do you think? Ha 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 ha. What if something like this? What is the current and the potential difference of each resistor? And this is the main aim of chapter 16, to figure out how to solve them. Let's take a look at series circuits. When a current flows around a closed loop via one path only, the circuit is called a series circuit. Now, is this a series circuit? Yes, it is a series circuit because the current only flows around the closed loop via one path only. Over here, the current can flow around a closed loop either by the red path or the blue path. We call such circuit a parallel circuit. Now, what do you think this is? Is this a series circuit or a parallel circuit? Well, it is both a series and parallel circuit. Now, let's take a look back at series circuit. Fact number 1. In a series circuit, the current flowing through all the components of the circuit, in this case the 3 resistors, is the same. So, in this case, if the current from the battery is 2 amperes, then all the ammeter readings will show 2 amperes. This is the case for series circuit. Now for the fact number 2, when you have resistors arranged in a series, the sum of the potential difference of each resistor is always equals to the EMF of the battery. This is simply conservation of energy. In this example, the EMF of the battery is 10 volts and the potential difference across R1 and R2 is 2 volts and 5 volts respectively. So what is the potential difference across R3? So if you apply what you just learned, the sum of potential difference in a series circuit is always equals to the EMF of the battery. Therefore, V3 is 3 volts. Now for fact number 3. When you have a lot of resistors arranged in a series circuit, the effective resistance is simply the sum of all the resistance of the resistors. So what is the meaning of effective resistance? By looking at the diagram, a circuit with many resistors is equivalent to a circuit with only one resistor, and the resistance of this resistor is simply the sum of all the resistance. Note that the current flowing through both circuits here is the same. Please look at textbook page 289 for the derivation. Now let's look at this example. We have a series circuit where the EMF of the battery is 10 volts. The resistors have resistance of 2 ohms, 2 ohms and 1 ohms, and we are asked to find the current I. Now since this is a series circuit, we can find the effective resistance, which is simply the sum of all the resistance, which is 5 ohms. Therefore, this circuit diagram can be simplified to the circuit drawn in point number 2, where the 3 resistors are just replaced by 1 resistor, which is a 10 ohm resistor. Therefore, using the formula I equals to V over R, we can find the current to be 1 ampere. So note that the current in both circuits are the same. So let's summarize. For a series circuit, the current flowing through all the components in the circuit is the same. Therefore, the ammeter reading A1, A2 and A3 should give the same value. Point number 2, the sum of potential difference across each component in a series circuit is always equal to the EMF of the battery. For the last point, when you have resistors arranged in a series circuit, the effective resistance is simply the sum of all the resistance of the resistor. Now let's have some thinking time. Consider the following circuit where the EMF of the battery is the same, 5 volts, and the second diagram has one more resistor than the other. So if I were to add more and more resistors to the series circuit, will the current increase or decrease or have the same value? What do you think? Now let us look at parallel circuits. Fact number 1, when the current from the battery goes to the red junction, it can either go to the R1 or R2. Therefore, this current will split into 2 currents. And when you add back the 2 currents, it will give you the original current from the battery. So, the current I1 that flows through R1 and the current I2 that flows through R2 will recombine at the red junction to produce the original current I. Now for fact number 2, when you have resistors arranged in parallel, the potential difference across each resistor is the same as the EMF of the battery. Now let's take a look at this question. We do not know the EMF of the battery, and we do not know the potential difference of R2, but we do know that the potential difference of R1 is 3 volts. So what is E and V2? The answer is, since this is a parallel circuit, both the EMF and V2 must both be 3 volts. Now, are you wondering why the V1 and V2 and the EMF are all equal? Now consider 2 charges, charge A and charge B, from the battery. They will receive 5 volts from the battery, and then when they travel to the blue junction, charge A will go to R1 while charge B will go to R2. Therefore, R1 will get 5 volts from charge A, and R2 will also get 5 volts from charge B. That is why in a parallel circuit, the potential difference of each resistor is the same as the EMF of the battery. Fun fact number 3. When you have resistors arranged in a parallel circuit, the effective resistance is simply 1 over R equals to 1 over R1 plus 1 over R2. Now consider the following example. What is the effective resistance R? Since the 3 resistors here are arranged in parallel, we can straight away apply the formula. 1 over R equals to 1 over R1 plus 1 over R2 plus 1 over R3. And then we invert it to get the effective resistance of 12 over 13. Now, inspect carefully the solution. The effective resistance of resistors in parallel is always smaller than the individual resistor. So, for many resistors in parallel, the effective resistance is simply 1 over R1 plus 1 over 2 plus so on and so forth. If you want to know how this formula is derived, please look at textbook page 292. Now please take a moment to see the difference between series and parallel circuits. Okay, now we have a battery with EMF of 5 volts attached to 2 identical light bulbs with equal resistance R. One diagram has them arranged in series and the other arranged in parallel. The conclusion from this is that 2 light bulbs or any 2 resistors which are arranged in parallel will always receive more current. Now please pause this video and take a moment to look at the calculation here. Therefore, bulbs which are arranged in parallel will shine more brightly than bulbs which are arranged in series. However, since they use more current, the battery will lose power more quickly. Now consider the following situation. What if when we have 2 light bulbs arranged in series and suddenly one of them is broken? Will the other light bulb still light up? The answer is no, because the circuit now is open and no current can flow to the other bulb. Now, what if when we have 2 bulbs arranged in parallel and suddenly one of them were to be broken? Will the other light bulb still light up? The answer is yes, because current can still flow through the other light bulb. The circuit is still closed. Now, please do questions 1, 2, 3 and 4 of this worksheet which are given to you.